Oh, so I'm going to be going through the maths of the button game on Steam. It is a game in which you press a button and it resets. There's a random chance that it just resets every time, and you've got to click it. See the highest number you can reach before it resets. The idea is it starts at 0.1 chance of it resetting and then increases by 1% each time. So we can write the probability it resets in the third time as 0.1. I might write it in a nice little one like this. So n x p x equals n. That is 1, 2, 3. I'll write in a dot 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 because there's infinite, obviously. The next one would be 0.99. So chance of failing on the first turn, and then the chance of it succeeding on the second turn, 0.02. And then the next one, 0.98 times 0.99 times 0.3. Alright, so we could rewrite that if we want to write p x greater than or equal to n. So the chance that it reaches that, so you haven't failed before it getting to n, your nth click, is equal to 99. Well, actually, I'll explain why once I've written it down, but maybe you don't need me to explain it. Times, factorial times 0.01 times n to the minus 1. So essentially what we're doing here is saying we're ignoring the chance of it succeeding on any turn, but just reaching that turn. So there's 100% chance you haven't failed by the first turn, then there's 99% chance you've not failed by the second turn, because that will just include the 0.01, and then you have here 0.98 times 0.99, and so on. So essentially it's essentially a factorial, but going 99 times 98, and then the next one will be 97, because it'll be just subtracting that, and so on. But obviously it's not 99 times 98 times 97, it's 0.99 times 0.98 times 0.97. So we need to divide by 100 for each term, which we've got 99 to convert. We've got like a 99 or a 98 or a 97 all the way down. So it's 0. that. So we have the 0.01 to the n minus 1. So here we get 0.99 instead of 99, because 2 minus 1 is 1, and so on. We're dividing by 100 times 100 for that one and 100 for that term, respectively. So that's how you get to that. And then from this we can also just write the px equals n. So this is just the same as it reaching n, and then timesing by the 0.01n, which is just reflective of that's a chance of success, or it resetting will cause success, even as not success, which you don't want it to reset. That is the chance of it resetting on any given turn, given it gets to that point, because it's increasing by 0.1 each time, so that's 0.01n, and so on. Well, not so on, but it just is 0.01n. So from this, we can find the expected value of the number of clicks. So we can write that as the expected value of x is equal to the sum of 100 to n equals 1. So we're summing essentially 1 times the probability of 1, 2 times the probability of 2, 3 times the probability of 3, in the same way you do the expected value for a dice is like 1 times a sixth, 2 times a sixth, 3 times a sixth, 4 times a sixth to find the mean value of a dice, but we're just doing it with this. So we get the previous, so we're looking at x equals n, not x greater than n, or equal to n, so 0.1 n squared, because we're timesing by n, and that's just an n before, times 99 factorial over 100 minus n factorial times 0.01 n to minus 1. And I can tell you that that is 12.21 by computation. Or, I mean, finding other ways, but just doing that sum via computers, what I did was quickest. So now we have the expected value, so that's how many clicks we get per turn roughly. So we can think about, well, the achievement in the game, the achievement which requires the most clicks is you have to click 30 times without it failing. So we can think about the probability of that. So the probability of that is x equals 30, because, and it's not x equals 30, it's greater than or equal to 30, because you still get the achievement if you get 31, 32, and so on. So we're not worried about the timesing by 0.3 to get the exact, because that's not necessary. It's just about reaching it, not getting exactly 30. So I forgot to. Just being an idiot. Sorry. Let's get that as 29. Alright. Well, and the expected number of turns, since this is geometric, because we would stop after we reach 30 or above, is 1 over this. And 1 over this is, let me just remember what it was. 128.35. So I'm going to write 1 over 128.35 for this probability. But the expected number of times you need to press is, the expected number of resets you have is 128, and so you would, or actually you need 129 goes on average to get 30. So from this, we might be able to, since we have the number of turns and the number of clicks per turn, this is not correct, but it's sort of fine. That's the number of clicks you'd expect to reach 30, because that's the number of turns and that's the number of expected clicks per turn. This is not correct exactly, because this sum is taking into account you reaching numbers above 30 as well, and obviously you're not, because if you'd reached above 30 it stops. So it's not exactly 12.21, but it's good enough. I mean, we'll keep it 21 for that, but just bear in mind that it's not correct, but it's approximately that. But it becomes especially bad, for instance, if you think about 4, well, it can't be 12.21 if you're trying to find the number of turns it reaches 4, because 12.21 by that point it's going to be over 4 and it has to be less than 4. Well, because only the last one can be above 4, so all the ones before must be lower than 4. But for 31, 30, it's fine. I suppose it's better approximation, because getting above 30 is already quite unlikely, so they're not really factored in that much anyway, but it's just something to bear in mind. So roughly I would say I'm making an assumption here that you make 3 clicks per second. I mean, the game does it doesn't let you click 100 times per second. There is a limiter, and I think it's about 3 clicks per second, but it might well be 4 or 2, so I don't think it's above 4. So I'm just going to say 3, go in the middle. This could be slightly higher. I'm already making an assumption there, so maybe it'll cancel out, you never know, because it's going to be slightly lower than that. And then we can times by 60, because then we can get the clicks per minute. And if I were to put that on my calculator quickly, 128.35 times 12.21 over 3 times 60. We get 8.7, which is the same as 8 minutes and 42 seconds. So that's how long you'd roughly, on average, how long you need to play the game before you get well, the 30 achievement. Well, I mean, there are other achievements for getting 1 and 3, which you need to take into account, but this is the one with the least. So if you play for 10 minutes, you're basically probably going to finish the game. But what if you don't want to just finish, you want to beat the record? So the record currently is 56, which is a lot. And so you might think, okay, so if I was to guess, you might think, oh, there's only 8 minutes to get 30. Well, it can't take that long to get 56, but yes, it can. Yes, it can. Anyway, I would just make your guesses in your head, and if you guess correct, fair enough. But yeah. So the expected value. Well, I'm just going to immediately write what it is. So it's it's 1 over the probability of x greater than or equal to 56 is equal to very large. Because obviously it is all the factorials. So it is 9, 4. Wait a minute. Sorry, I need to rerun my program. 56. It's 6, 4, 7, 3, 5, 5, 7, 5, 9. 5, 5, 7, 5, 9 point. I might as well write the points in because it's times 100. 0.322. All right, and this is not this is greater than. I already put the 57, so that's 1 over greater than 57 because you wouldn't beat the record if you only got 56. So that's the expected number of turns, which is a hell of a lot. Yeah, it is. That's. Well, I don't know. I wrote that's 6. That's the. I've written 9 there for some reason. My bad. Let me just make sure that's correct. I don't want to get this wrong. 7, 3, 5, 5, 7, 5, 9. Yep, that's fine. And then, so we can times this by 5, 5, 7, 5, 9.322 times 12.21. This 12.21 has basically become a really good approximation now. Like, it's not absolutely perfect, but it's basically there. And then we're going to times this, well, divide it by 3 times 60. I mean, let's just go straight to 3,600 times 24 times 365 because it's massive. And that roughly gets you about, let's just again, 83.5 or something. So we'll just say 84 years roughly. Roughly about 84 years, 83.5 years. So if you're clicking 3 times per second for 84 years, that's on average, that's the average amount of time it would take for you to break this record, which is utterly ridiculous. If you want to, you can try with your 50. Try with the 55. I see what the current record was to reach that record. That would be 55. So that instead that's 284. 284. 836. 836. 534. So that's significant. This would be for the current record, so the person currently has. And let me just quickly stick that into my calculator. 8436,534 times 12.21 over 3 times 364 times 365. So that's only equal to about 37 years, so significantly less. significantly less time you need to spend. Yeah, and obviously that's going to go down pretty quickly after that. So the person got incredibly lucky because they did not spend 37 years clicking. Or I mean, they could have. I don't know if there's anything where you can change the probability in the game. I haven't really looked into it. Or they might have done hacking to run multiple at the same time. But it's a long time. Let's just say that. I would encourage people to experiment with this. I don't know if anyone wants to think about beating their high scores or how long they'd spend to beat or get equal, or how if they got below what was expected or above what was expected for their current high score is. See if they're ahead of schedule or behind in terms of what they have already. But I would say for the lower numbers, just be very careful about this 12.21 because you're going to want to subtract the ones which are not missing out because that becomes increasingly more significant. But anyway, 84 years and goodbye.